Today we are on the beach of the Georgeville Pluton, and those of you who've been already on the field school, you may remember this beach. This is our introductory exercise. Those who are going to be on field school, then this is where you're going to start. There are a number of interesting features that we can see here, and first of all, again, we have different rock types. So I am sitting on a pinkish rock, light pink rock. Just behind me, you can see that there are some dark rocks coming out of the water, and in front of me there is another dark rock, and in addition to that we can also see some variation of the pink rock that I'm sitting on, and we're going to walk around and look and explore the differences within this pink rock. But our first question is what it is. So this rock is again very hard. It's hard to scratch. We can see that again it's a very silica rich rock. Actually my hammer is not able to scratch it at all. So, and we don't see any particular fabrics in this rock, but we can see that all the grains in this rock can be visible with our naked eye. So this is a pheneritic rock. We don't have a fine grain matrix as we saw in rhyolite and in the basalt. We see that all grains are maybe from 1 to 3 millimeters in size. So this is a pheneritic rock, and this rock is an intrusive rock because all the grains are relatively large. So the rock is intrusive, and it's a light colored, so it's a felsic rock. If you look on our diagram, it will place us somewhere in the field of the granitoids. However, you have a sample of this rock. So I want you to determine the mineralogy, the proportions of the minerals, and to come up with a proper name for this rock. But this is somewhere in the group of granitoids. So we'll call it granitoid for now, for our video. So this is the first dark rock that we see on this outcrop, and it continues all the way into the vegetation and forms a contact with our pink rock behind me. So this is a country rock in which the intrusion was emplaced. Let's look close on the features in this rock. So, this is a dark rock, and it's relatively solid, but it's not as difficult to break it as the basalt that we saw in the other spot. It's also a little bit easier to scratch. So again, it's not a sedimentary rock, definitely. It's very, very fine grain, and it shows no grains, no features. What is also important that it shows no vesicles. So it's quite different from the basalt that we saw yesterday. But what it does show, if we look on these gray continuous features, this is the bedding that was preserved in this rock during metamorphism. So this is the original bedding that tells us that this rock is metasedimentary. So once upon a time it was a sedimentary rock that was metamorphosed, and it's not of an igneous origin, and then our granitoid intrusion was emplaced in this rock, and we're going to examine the nature of the contact between the two. The contact is very sharp between the intrusion and the country rock. So basically, this is just a line where we can put the finger on the contact. What does it tell us? First of all, that emplacement of this intrusion was very shallow, so the temperature contrast between the intrusion and the country rock was very large. So the country rocks were close to the surface, and so they were very cool, much cooler than the intrusion. So it's a shallow intrusion. Second thing, that also such a sharp contact with no chemical interaction between the magma and the country rock, with no gradational changes into the country rock, suggests that this intrusion was probably not water-rich intrusion. It probably didn't have too much fluid to slowly release and to interact and chemically change the country rock. We can also see that there is a baking effect on the country rock. And we stepped a little bit further from the contact and we see something different happening in this intrusion. The color is still the same, and the two main minerals, quartz and alkali feldspar, are still the same. But what is different, that you can see that the size of the crystals changed a lot. Our granitoid, where we started, and the sample that you have is relatively fine-grained. So you can see the grains with your eye, but they are relatively small in a range of a couple of millimeters. Whereas here we see that some of the individual grains are really huge. So the huge quartz sitting in the large crystals, surrounded by large crystals of alkali feldspar. So this rock is called pegmatite. And pegmatite, in this case, it's a small body formed within the intrusion. The origin of pegmatite is related to the fluid. By the end of crystallization, when anhydrous minerals such as quartz, feldspars form, the content of water in the melt starts to increase, because as these minerals form, they don't take water, so the percentage of water in the melt is increasing towards the end of crystallization. And at some point, the melt becomes very rich in water. And water really helps to enhance processes of element diffusion through the melt. So when you have fast diffusion, then any crystallization center is able to get all the constituents for the mineral to grow very fast. And crystals are able to form very large size. So some of the crystals coming from pegmatites are really huge. So here we can really see association between the main body of intrusion and this small body of pegmatite within it. It also tells us that we are somewhere closer to the top of the intrusion, which makes sense if we look on extremely sharp contact with the country rock. Here we're standing in the country rock, very close to the contact with the intrusion. And we see this veinlet coming from the intrusion into the country rock. So it's an apophysis that actually cuts into the country rock. And if we compare, again, the composition of this veinlet, it's the same as our intrusion, but the grain size is even smaller than the grain size of the main intrusion, and of course much smaller than the grain size of the pegmatite. So these are so-called applied dikes that are very commonly surrounding, again, the top part of the intrusion. Here we're looking on the second dark rock, and we can see that unlike our first rock, that was a metasedimentary metamorphic rock, this rock is forming a dike that is vertical and it's cutting through our granitoid. So we see that it continues all the way from the water line and into the cliff and into the vegetation. So it's a long continuous feature. We can see that the contact again is very sharp between the dike and between the granitoid. And here we can explore a number of processes. So first of all, looking on the very dark color, fine grain matrix of this dike, we know that it's a mafic dike, so the composition was similar to basalt. However, for these hypabyssal rocks that don't erupt at the surface but solidify very close to the surface, typically they call dolerite or diabase. But the composition is very similar, the same as basalt or gabbro. It's just a hypabyssal rock. So this mafic dike cuts through our granitoid, and one thing that we have to remember, that the temperature of mafic magma and felsic magma is very different. So mafic magma forms at around 1200 degrees, so the eruption temperature close to 1200 degrees, whereas the temperature of the felsic magma is somewhere on a range 700-800. But we can see from the configuration of the contact that by the time this mafic magma was intruding, the granitoid was completely solid. Because if we look closer on the contact between the two, we see that our granitoid is fractured as the magma get emplaced, and it's fractured, showing the brittle fracturing in a brittle way, like a solid body. We can see very thin ventlets of the mafic magma intruding in the fractures in the granitoid. We can also see pieces of the granitoid of very angular shape that are broken and involved in the mafic magma as it was intruding in. So all of these relationships tell us that the mafic magma came quite after the granitoid. So granitoid had all the time to cool down, to crystallize, and the temperature contrast, of course, also was very high between the very hot mafic magma and pretty much cool down the granitoid. So what we can expect two types of features associated with the contact. So if we focus on the dike, then we can see that the grain size is quite different between the dike very close to the contact with the granitoid, so-called chill zone, where the magma had to cool down and crystallize very fast because it was in contact with already cold granitoid. And in the middle, the grain size is quite a bit larger, so we can actually start to see individual crystals of pyroxene and plagioclase in the middle of the dike. If we now look on the granitoid, the main effect is the baking by the hot magma, and the only representation here of this process is the change in the color. We can see that everywhere along the contact, and the pieces that actually got entrained in mafic magma, they develop this red color, quite a strong red color, whereas the rest of the granitoid is very light pinkish. Let us zoom up what we saw on this outcrop. I am standing on this pink rock, the granitoid intrusion, that was emplaced in the metasedimentary metamorphic country rocks. And this outcrop allows us to examine the field relationship that are very specific for igneous rocks. We remember that unlike sedimentary, igneous rocks show cross-cutting relationship with the country rocks. They show inconformities due to cutting through the country rocks through which they intrude, and this is clearly demonstrated by the contact between the metasedimentary metamorphic rock and between our intrusion. So we see very sharp contact that cuts through all the bedding and all the features in the country rock. Also, by the very sharp nature of the contact, we can say that we standing somewhere close to the top of the intrusion, and also the intrusion was very shallow. So there was a very large temperature contrast between the country rock and the intrusion. We can also see that the intrusion was relatively dry because it didn't give away too much fluid to produce significant chemical changes in the country rock. We can also see more of this igneous contact relationship by the contact between the later mafic dike that cut and emplaced into our granitoid intrusion. We can see cross-cutting relationship. We can see that dike cuts through the intrusion. We can see how the pieces of the granitoid are broken and entrained into this mafic magma. We can also see the nature of the contact, that a very hot mafic magma produced baking effect along the contact on the granitoid by changing color into red. And we can also say by the nature of the contact that the dike was very much later than the intrusion. So the intrusion was solid. It was breaking in a brittle way as a solid body as it was intruded by this mafic magma. We also could examine some variation within the intrusion. So we saw body of pegmatite with very large crystals, very large grain size, that suggests that we see it in somewhere close to the roof zone, to the cupola of the intrusion, where the fluid gets accumulated by the end of crystallization. And we can also see applied dikes shooting into the country rocks with a very fine grain sugary texture.